Hello, my name is René Chutura and I present Hagrid, a method to gridify scatterplots with the help of two space-filling curves, the Hilbert and the Gosper curve. With dimensionality reduction, we are able to visualize high-dimensional data in scatterplots. Data in a scatterplot is encoded by the position of the dots. The proximity of the dots encodes the similarity of the high-dimensional data. A possible enrichment for scatterplots is replacing dots with meaningful glyphs or images for additional information. Here, for instance, is a scatterplot of a UMAP projection of the iris dataset. The iris dataset consists of measurements of 3 species of iris flowers with 50 exemplars each. The 4 dimensions are the length and the width of the sepals and the petals of the individual exemplars. The values can be encoded as a glyph, which looks for instance like that. With this size of the glyphs, overlaps occur. With a slightly smaller glyph size, overlap still occur. With even smaller glyphs, the glyphs are not readable anymore and thus lost their purpose, and still a few glyphs overlap. If the glyphs are aligned on a grid, no overlap occur anymore. When possible, a scatterplot can be enriched with images. The Coil 100 dataset, for instance, consists of photos of objects at various rotations. Projected with UMAP and the points drawn as their image, a lot of overlap occur. On the gridified version of the scatterplot, no overlap occur anymore. For gridifying the scatterplots in the examples before, we used our technique called Hagrid, which stands for Hilbert and Gosper curve-based grids. The Hilbert and the Gosper curve are space-filling curves with the properties of being self-avoiding and self-similar. They have recursive construction rules, are neighborhood preserving, and have a bijective mapping function from the curve to 2D. The starting pattern of the Hilbert curve has an U-shape. At the next level, the starting pattern gets rotated and repeated 4 times. At the next level, the last pattern gets rotated and repeated again, and so on. A starting pattern of the Gosper curve could look like this. At the next level, the starting pattern gets rotated and repeated 7 times. Here I want to illustrate Hagrid with a simple example of another scatterplot with 10 images where some of them overlap. In the first step, a level of the Hilbert curve gets selected, which provides enough grid cells for the scatterplot, and the points get mapped to fit into the grid. In the next step, the images get placed onto the curve. If a spot is already occupied by another image, the method looks at the predecessors and successors of the spot to find an empty one. The neighborhood preservation property of the space-filling curve ensures that a spot near the original spot on the curve is also close in 2D. The flowers image, the first image, gets placed on the first spot without a collision. The cow image gets placed on the second spot, also without a collision. The dog image should go to the second spot, but is occupied by the cow. After some collisions, the dog image gets placed on the third spot. The child image gets placed on a later spot without a collision. The image of a man gets placed on the 13th spot, also without a collision. Here, the algorithm found 2 empty and valid spots, so the image gets placed where the image is closer to its original position in 2D. The image this image should go to the 10th spot. After some collisions, the cow image gets placed on the 11th spot. This image should go on the first spot, but it doesn't have empty and valid spots preceding. So after some collisions and looking forward, the training image gets placed on the 4th spot. The image of a woman gets placed on the 5th spot without a collision. This image should go to the 9th spot, but gets placed on the 8th spot after some collisions. So now are all images placed onto the curve, and each image owns an own spot. In the last step, the images get moved back to 2D, which results in an overlap-free scatterplot where the grid positions of the images are not too far from the original positions. First, we did a theoretical runtime evaluation. The runtime is mainly dependent on the number of data points to gridify. The Hilbert and Gosper curves have recursive construction rules, and they start with a pattern with a number of available spots. The Hilbert curve with 4 and the Gosper curve with 7. Each level deeper, the number of available spots gets multiplied by, in the case of the Hilbert curve, by 4, and in the case of the Gosper curve, by 7. So the minimum level for the space filling curve with enough spots for the data can be computed with the log to the base of 4 or 7 of n, the number of points, and this result rounded up to the next integer. The algorithm to compute one index needs O log n runtime. Algorithm 1 just places images if the respective spot is empty. If not, it calls a second algorithm for resolving the collision and placing the image. Computing the spot for 1 point need O log n runtime, so placing all n points need n log n runtime. The runtime for the collision is in the best case O1 if the next or the previous spot is available. In the worst case, algorithm 2 finds all already occupied spots until it finds an empty spot. So algorithm 2 has in the worst case a runtime of On. So all in all, the best case for Hagrid is On log n, and the worst case is On squared log n. We created randomly uniformly distributed placed points of dataset sizes from 1000 points up to 10,000 points with a step size of 100 points. Here we measured the runtimes and number of collisions for Hagrid gridifying those scatterplots using the Hilbert curve and the Gosper curve. We computed the grid layouts for each dataset 20 times, shown as colored dots in the chart, and the lines show the averages of those measurements for the used space filling curve. The second chart shows the number of collisions happened. Here we used a log scale. The spikes appear when the respective space filling curve reach the maximum allowed points for the used level. The chart shows that, as expected, more collisions increase the runtime slightly. We also compared Hagrid to other techniques, with DGrid, which produces space filling layouts, with SMWG, which is used usually for creating grid layouts of geographical areas with a strong focus on quality, and CMDS, which also produces grid layouts as our approach at seemingly much higher runtimes. We used various dataset sizes with a wide range of sizes, computed various dimensionality reduced projections For evaluation, we used 5 different metrics to measure those resulting grid layouts. We used NP, the neighborhood preservation, CC, the cross correlation, SI, the size increase, ED, the Euclidean distances, and also the runtime. Hagrid is shown here in purples and the other gridifying techniques with yellow and orange hues. The chart shows small box plots with the mean result as white line. Here on the right side is again the comparison result of the runtimes. We show SMWG only for the smallest dataset, because the runtimes for those sizes are already very high. CMDS for the first two groups of dataset sizes, which has a better runtime than SMWG, but is apparently still very slow. DGrid is very fast, but through all dataset sizes roughly 4 times slower than Hagrid. I use for illustration a bigger subset of the already previous used Coil 100 dataset, where Hagrid keeps the global structure, whereas DGrid, which has a space-filling approach, fills the space, which has the advantage of bigger grid cells, but comes with the loss of the global structure of the scatterplot. SMWG has the best results for neighborhood preservation for the smallest dataset sizes. Neighborhood preservation is a very important metric for evaluating techniques for gridifying geographical areas. CMDS has the best results for the next bigger dataset sizes, and after that Hagrid has the best results. On the left, each single point of the dataset is colored by the value of the neighborhood preservation, where orange means no neighborhood preservation of the point, and purple complete neighborhood preservation at that point. With the cross-correlation metric, Hagrid has the best results for all dataset sizes. An example on the left, the Hagrid results have very good values, and DGrid has one spot with worse cross-correlation values. The lines on the left here connect the original positions of a point to its gridified position, and the color shows the Euclidean distance between those two positions. Hagrid, as throughout all dataset sizes, has the best results for the Euclidean distance metric. Hagrid has some limitations. There are very dense areas in some areas in a scatterplot, which produces artifacts in the final layout. The dots here are colored by the neighborhood preservation metric. This is probably a problem for most gridifying algorithms. Hagrid does not work well with outliers, and even worse with extreme outliers. But those are examples where you probably have to rethink the dimensionality reduction output in the first place. There are two implementations of Hagrid, one in Python and one in JavaScript. We did the evaluation with the Python implementation, and this presentation, for example, was made with the JavaScript Hagrid library. Thank you.